So in this video, we're going to talk about how to calculate the charge and the voltage across a capacitor if we have capacitors in series and parallel combinations. So let's start with this problem. What's the first thing we need to do in order to calculate the charge on every capacitor? Now the first thing we need to do is calculate the equivalent capacitance of the entire circuit. Now whenever you have two capacitors in parallel with each other, the total capacitance, or the equivalent capacitance, is simply the sum of those two capacitors. So it's going to be C2 plus C3 just for this network. So we can replace that with a 20 microfarad capacitor. So now we have this circuit. We have a 10 microfarad capacitor in series with a 20, which is in series with another 20. Now, whenever you have two capacitors in series with each other, and if they have the same value, the equivalent capacitance of those two capacitors is going to be half of their individual values. So half of 20 is 10. So I can replace these two capacitors with a single 10 microfarad capacitor. Now this capacitor is also 10. So the equivalent capacitance of these two will be 5. So that's the equivalent capacitance of the entire circuit. It's 5 microfarads. Now, if you wish to confirm the answer, you can use the formula. So let's use it with these three capacitors in series. So the equivalent capacitance is going to be 1 over C1 plus 1 over C2 plus 1 over C3 raised to the minus 1. So 1 over 10 plus 1 over 20 plus 1 over 20 raised to the minus 1, that is equal to 5. Now if you don't have access to a calculator, here's what you need to do. Multiply this fraction by 2 over 2 to get common denominators. So that becomes 2 over 20 plus 1 over 20 plus 1 over 20. And then add the numerators of the fractions. So 2 plus 1 plus 1 is 4. So what we now have is 4 over 20 raised to the minus 1. Now to raise something to the negative 1 power, you need to flip the fraction. So it becomes 20 over 4, which is equal to 5. So that's the equivalent capacitance of the circuit. Now the next thing that you need to know is that the charge for any capacitors in series is the same for each capacitor in series. For capacitors in parallel, the voltage is the same across each of those capacitors. Now, what we have is three capacitors in series. We have C1, which is 10 microfarads, and that's in series with the equivalent capacitance of those two, which is 20, and that's in series with C4, which is also 20. So let's calculate the charge on each of these three capacitors. So to do that, use this formula. The charge of every capacitor in series is going to be the equivalent capacitance times the voltage, and that is the voltage of the battery. So the equivalent capacitance is 5 microfarads, and the voltage is 100 volts. So 5 microfarads times 100 is equal to 500 microcoulombs. So that's the charge on each of these capacitors. So the charge on C1 is 500 microcoulombs, and the charge on C4 is also 500 microcoulombs. Now what about the charge on C2 and C3? Because those are parallel to each other. The total charge of these two is 500 microcoulombs, but how can we calculate the individual charges? So to calculate Q2, it's going to be the total charge of just this network multiplied by C2 divided by the total capacitance of that network, which is C2 plus C3. So the total charge of these two capacitors is 500 microcoulombs. Now C2 is 15 microfarads, And C2 plus C3, that's 15 plus 5, which is 20 microfarads. So it's going to be 500 times 15 over 20. And so the charge on C2 is 375 microcoulombs. Now to calculate it on C3, we're just going to use a different variation of that formula. So it's going to be Q3 is equal to the total charge for that network times C3 divided by C2 plus C3. So that's 500 microcoulombs times C3, which is 5. C2 plus C3 is 20. So it's 500 times 5 over 20. So then C3 has a charge of 125 microcoulombs. Notice that these two numbers add up to 500, which tells us that we're on the right track. So now that we have the charge on every capacitor, we can calculate the voltage across each capacitor. So let's start with the voltage across C1. So we know that Q1 is equal to C1 times V1. So the voltage is going to be the charge divided by the capacitance. So the charge is 500 microcoulombs and the capacitance is 10 microfarads. So the unit micro will cancel. And so 500 divided by 10 will give us a voltage of 50 volts across C1. Now let's calculate the voltage across C3. So V3 is going to be Q3 over C3. So the charge is 125 microcoulombs divided by 5 microfarads. So 125 divided by 5 will give us a voltage of 25 volts. Now notice that C2 and C3 are in parallel with each other, which means they should have the same voltage. So to calculate the voltage across C2, it's going to be V2, which is Q2 divided by C2. So that's 375 microcoulombs divided by a capacitance of 15 microfarads. So 375 divided by 15 will give us the same voltage of 25 volts. Now to calculate the voltage across C4, it's going to be Q4 divided by C4. And so the charge is 500 microcoulombs and the capacitance is 20 microfarads. So 500 divided by 20 will give us a voltage of 25 volts. Now notice that the voltage across the capacitors adds up to the voltage of the battery, meaning that 25 plus 25 plus 50 adds up to 100. So that tells us that we're on the right track. Everything that we've done so far is correct. So now that we have the charge on each capacitor and the voltage across each capacitor, let's calculate the potential energy stored in one of the capacitors. So let's say if we want to calculate the potential energy stored in C3, how much is it? And what equations can we use to calculate it? There's three formulas that we could use. It's 1/2 CV squared. We could also use 1/2 QV, or we could use 1/2 Q squared divided by C. So I'm going to use the first one, 1/2 CV squared. So for C3, it's going to be 1/2 times a capacitance of 5 microfarads, which is 5 times 10 to the minus 6. And then the voltage is 25 volts. So it's 0.5 times 5 times 10 to the minus 6 times 25 squared. And so the potential energy across that capacitor is 0.00156 joules, which you can say it's 1.56 millijoules. Now what about the energy stored in C1? Let's find that answer as well. So this time I'm going to use this equation. So it's 1/2 QV. The charge on C1 is 500 microcoulombs. So that's 500 times 10 to the minus 6. And the voltage across it is 50 volts. So the energy stored in that capacitor is 0.0125 joules, which is 12.5 millijoules if you multiply it by 1,000. So now you know how to calculate the potential energy of any capacitor in a circuit like this, and you also know how to calculate the charge on every capacitor and the voltage across every capacitor. Now let's try another similar problem. So let's say if we have a battery attached to a capacitor, which is in series with a network of capacitors. So let's say the circuit looks like this. And so this is going to be a 96-volt battery. Here we have the positive terminal and the negative terminal. And let's call this C1, C2, C3, C4. Now let's say C1 has a capacitance of 100 microfarads. C3 is going to be 40 microfarads. And C4, 120 microfarads. And C2, we're going to assign it a value of 70 microfarads. So feel free to pause the video. Go ahead and solve this problem. Calculate the charge on every capacitor and also the voltage across each capacitor. So step 1 is we need to calculate the equivalent capacitance of the entire circuit. And then once we have that, just like before, we're going to calculate the charge on every capacitor. And then finally, we'll calculate the voltage across each capacitor. So C3 and C4 are in series with each other. So to calculate the equivalent capacitance of two capacitors in series, it's going to be 1 over 40 plus 1 over 120 raised to the minus 1. Now we're going to multiply this fraction by 3 over 3. So then it becomes 3 over 120 plus 1 over 120. And so 3 plus 1 is 4. And so this becomes 4 over 120 raised to the minus 1, which is 120 over 4. And so the equivalent capacitance of C3 and C4 is 30 microfarads. And so that is in parallel with C2, which is a 70 microfarad capacitor. So combined, the 30 and the 70 is 100. When they're in parallel, the equivalent capacitance is the sum of the individual capacitors. So we can replace this with a single capacitor of 100 microfarads. And this is in series with this other capacitor, which is also 100 microfarads. So the equivalent capacitance of two capacitors in series that have the same value is going to be half of 100. So that's going to be 50. To confirm that answer, you could do this. You could say it's 1 over 100 plus 1 over 100 raised to the minus 1. 1 plus 1 is 2, so this becomes 2 over 100. And if we flip it, it becomes 100 divided by 2, which is 50. So the equivalent capacitance of all four capacitors is 50 microfarads. So that's step 1, is to calculate this value. Now let's calculate the charge on this capacitor and the equivalent capacitance of this network, which is that value. Now keep in mind the charge for two capacitors in series will be the same. So Q is going to equal CV. So it's the equivalent capacitance of 50 microfarads times the voltage of the entire battery or the entire circuit, and that's 96 volts. So let's go ahead and take 50 and multiply by 96. So this is going to be 4,800 microcoulombs, because this was in microfarads. So this is 4,800 microcoulombs, and this is also 4,800 microcoulombs. So we have the value for C1. We can write it here. Now we need to focus on the other three capacitors. We have the total charge on all three of those capacitors. So now we need to break it down. So this network is equivalent to these two capacitors in parallel. So that's C2, which is 70, and that's the combined effect of C3 and C4, which earlier we got was 30. Now to calculate the charge on this capacitor, it's going to be the total charge, which is 4,800 microcoulombs, times the value of this capacitor, which is 70, divided by the total capacitance of 70 plus 30, which is 100 for that network. So it's going to be 4,800 divided by, times 70 divided by 100. So C2 has a charge of 3,360 microcoulombs. Now let's calculate the total charge on the 30 microfarad. So it's 4,800 microcoulombs multiplied by 30 divided by the total of 100. So it's 4,800 times 30 over 100, and so this is 1440, and this was 3360. So these two have to add up to 4,800. So whenever you have two capacitors in parallel, the individual charges on each capacitor has to add up to the total charge on the whole network of the capacitors in parallel to each other. Now, how can we use this value to calculate the charge on C3 and C4? Now remember, whenever you have two capacitors in parallel, the voltage is the same across those two capacitors. If you have two capacitors in series, the charge is the same. So the charge on C3 is the same as the charge on C4, which is the same as the charge on the equivalent capacitance of C3 and C4. So what this means is that the charge on C3 and C4 is equal to this number. So it's 1440 microcoulombs. So now we have the charge on every capacitor. Now let's calculate the voltage across each capacitor. And let's see if it adds up to 96. So let's start with C1. So the voltage is going to be the charge divided by the capacitance. So the charge is 4,800 microcoulombs, and the capacitance is 100 microfarads. So 4,800 divided by 100 is 48 volts. Now let's calculate the voltage across C3. So V3 is going to be Q3 divided by C3, and so that's 1440 microcoulombs divided by 40 microfarads. And so this will give us 36 volts across the 40 microfarad capacitor. Now let's do the same thing for C4. So V4 is Q4 divided by C4, and so that's 1440 microcoulombs over 120 microfarads. And so that's going to give us a voltage of 12 volts. Now notice that the voltage across these two capacitors must be equal to the voltage across that capacitor because they're parallel to each other. So 36 plus 12 is 48. So we should get a voltage of 48 across C2. So V2 is Q2 divided by C2. And so that's 3360 divided by 70 microfarads. And so that gives us a voltage of 48 volts. So if we add these three values, 48 plus 36 plus 12, that gives us the voltage of the battery. Now you can't add this as well because that is already in parallel with those two values, so you can't add it twice. So that's it for this problem. You now have the voltage across every capacitor and a charge on each capacitor. Now let's work on one final example. So let's say that the voltage of the battery, let me pick a good number. Let's say it's 400 volts. And let's call this C1, C2, C3, C4, and C5. So let's say that C1 is 300 microfarads, and C2, that's going to be 60 microfarads. Let's make C3 200 microfarads. C4 is going to be 100, and let's make C5 100. So calculate the charge on every capacitor as well as the voltage across each capacitor. So let's focus on this network because we have 3 capacitors in series. So these 2 are in series, and so the equivalent capacitance of that will be 50. And the 50 capacitor is in series with a 200. So to calculate the equivalent capacitance of that, it's going to be 1 over 50 plus 1 over 200. Now let's multiply this by 4 over 4. So it becomes 4 over 200 plus 1 over 200. 4 plus 1 is 5, so it's 5 over 200. And if we flip it, it becomes 200 over 5, which is 40. So let's draw the circuit that we now have. So here's C1, it's 300 microfarads. C2 is 60. And these 3 capacitors combined is 40. So now notice that the 60 is in parallel with the 40. So we can add those 2. And so that gives us an equivalent capacitance of 100 microfarads, which is in series with the 300 microfarad capacitor. And so the equivalent capacitance is going to be 1 over 300 plus 1 over 100 raised to the minus 1. So let's multiply this by 3 over 3. So it's 1 over 300 plus 3 over 300. And so 1 plus 3 is 4. So we have 4 over 300, which becomes 300 over 4. And so the equivalent capacitance of the entire network is 300 divided by 4, which is 75 microfarads. So now let's calculate the charge. So Q is equal to CV. So that's going to be 75 microfarads multiplied by the voltage of the battery, which is 400 volts. So 75 times 400 is 30,000 microcoulombs. So I'm going to write that as, I could say it's 30 millicoulombs. Or you could say it's 0.03 coulombs. If you write it as 30,000 times 10 to the minus 6, that's 0.03 coulombs. But I prefer to keep it in microcoulombs because when I divide microcoulombs by microfarads, it's going to give me the unit in voltage. So I don't have to change anything. So I'm going to keep it as 30,000. Now let's work backwards. C1, which is 300 microfarads, that was in series with the equivalent network of those 4 capacitors, which we found was 100. So because these 2 capacitors are in series, and we got an equivalent capacitance of 75 microfarads, which led to a charge of 30,000 microcoulombs, each of these capacitors have this charge. So we have the charge on C1. So that's 30,000 microcoulombs. Now let's focus on this network. So this capacitor can be broken down into two capacitors, one of which was 60, and the other is the equivalent of these three capacitors, which we know was 40. Now, because these two capacitors are in parallel with each other, the charges on these two capacitors must add to 30,000. So to calculate the charge on the 60 microfarad, it's going to be 30,000 times 60 divided by the sum of these two values, 60 plus 40, which is 100. So it's 60% of 30,000. And so that comes out to 18,000 on this one. And so the other one is going to be 30,000 minus 18,000, which is 12,000. You can also do 30,000 times 40 divided by 100. That will give you 12,000. So across C2, the charge is 18,000 microcoulombs. Now let's focus on the 40 microfarad capacitor. We got that value from these three capacitors in series. And keep in mind, the charge of every capacitor in series is the same. And it's the same as the charge on the equivalent capacitor. So that means that Q is equal to Q3, which is equal to Q4, and that's equal to Q5. And this is Q. So each of those other capacitors in series with each other's has the same charge of 18,000. I mean, not 18,000, but 12,000 microcoulombs. So now we have the charge on every capacitor. So we can calculate the voltage across each capacitor. So let's start with this one. So V1 is going to be Q1 divided by C1. So that's 30,000 microcoulombs divided by 300 microfarads. So 30,000 divided by 300. What we can do is cancel two zeros, and so it becomes 300 divided by 3, which is 100. So we have 100 volts across C1. Now let's calculate the voltage across C2. So V2 is going to be Q2 over C2. So that's 18,000 microcoulombs divided by 60 microfarads. So we can cancel a 0, and so it becomes 1800 divided by 6, which is 300. So that's the voltage across C2. Now notice that if we go around this loop, the sum of the voltage drops, or the sum of the voltages around that loop, is 0 according to Kirchhoff's voltage law. So another way of saying it is that the voltage of the capacitors across that loop is equal to the voltage of the battery. So 100 plus 300 adds up to 400. So that means we're on the right track. Now let's look at C2. C2 is 300, which means these three capacitors must also add up to 300. Now let's calculate the voltage across C3. So V3 is going to be Q3 over C3. And so that's 12,000 microcoulombs divided by 200 microfarads. So the voltage across C3 is 60 volts. Now the voltage across V4, that's going to be Q4 divided by C4. So the charge is the same as 12,000, but this time we're dividing it by 100 microfarads. Because there's less capacitance, the voltage will be greater. So it's 12,000 divided by 100, and so it's going to be twice the value of this capacitor. So it's 120 volts. Now these capacitors have the same capacitance and the same charge. So if we do 12,000 divided by 100 again, that's going to give us the same voltage of 120 volts. So notice if we add 60 plus 120 plus 120, that's going to add up to 300. Because the potentials at these 2 points has to be 300. That's the voltage across the capacitor. And if you go in this direction, it needs to change by 300 as well. So let's say if this is point A and this is point B, C, D, E, and F. Let's say we wanted to calculate the electric potential at every point. And let's say that A is 0 volts. Going in this direction, that's going to be a voltage lift of 400 volts. Now this capacitor is going to have a positive charge because it's next to that terminal. And this is going to have a negative charge. And so this is going to be positive. This is going to be negative because it's next to this sign. This will be negative, and that will be positive, and so forth. Now notice that there's no element between A and B. So the potential at A is the same as the potential at B, which is 0. Now if we go in this direction, we're going towards the positive side of the capacitor, so that's going to be a voltage lift. So the potential at E is going to be 300 volts higher than the potential at B. So E is going to be 300 volts. Now if we were to go from, let's say, E to F, notice that we're going towards the positive terminal of the capacitor, so that will be a voltage lift of 100. 300 plus 100 will take us to 400. So we can see that makes sense. Now let's go from B to C. So we're going towards the positive terminal, so that's another voltage lift. And the potential across C5 is 120. So the potential at C is going to be 0 plus 120. So that's going to be 120 volts. So now if we move from C to D, it's another voltage lift of 120. And so the potential at point D is going to be 120 plus this 120, so that's 240 volts. Now, if we travel from D to E, we're going towards the positive terminal of this capacitor, so that's another voltage lift, and it's going to increase by 60. So 240 plus 60 will give us 300. And so we can see how everything works out in this problem. So that's how you can calculate the electric potential at every point across this capacitor network.